Hi all, let's move into our next session. So this is the session 7 we are looking into. So today we will try to look into some new topics and we will try to solve using some other methods of for the truth table functions. So and this is with respect to the previous session what we have discussed. So it's a Quinn-McCluskey method, and for this this we have already discussed topic, but based on the topic, please try to solve these problems. Here we have two problems. These are main terms, and please go through that so that you will have a better idea about it. And let's move on to the next topic, which is called Quinn-McCluskey Petrix Quinn-McCluskey method with Petrix method. So you might be wondering like what is Petrix method? Already as of now till now we have seen K-map and using Boolean algebra we are trying to solve the truth table functionality, truth tables solution. We are trying to find out the true solution for a truth table by using Boolean algebra, then K-map, then Quinn-McCluskey method. Then now we are heading towards Petrix methods, and this is used when we have a more number of inputs frequently. Okay, and to obtain good results. Okay, Petrix method is a technique for determining all minimum sum of product solution from a prime implication chart. So you need to remember this topic. Minimum number of product solutions from a prime implicant charts, and always our point is to discover minimum sum of product solutions, but here still we are trying to go further, like how it can be still it can be simplified further. Okay, as a number of variable increases, the number of prime implicants and the complexity of the prime implicant chart may increase significantly. That's as we have already known it, prime implicants. So by using k-maps and all, so whenever the number of implicants increases, so even the to obtain the exact solution of that K-map will also increases. In such cases, large amount of trial and error may be required to find the minimum solution. That's true, right? So as the number of input, as the number of implement prime implicants increases, so and also some of it is directly proportional to the uh, like trial, and we will be having it is directly proportional to error problem, which may lead into error problem. Okay, Petrix method is one more systematic way of finding all the minimum solutions from a prime implicant charts than used method previously, and it's a different method, but you need to be very careful and you should understand like how it can be done. So once again, it's a somewhat a difficult concept, I can say, not a too difficult one, but you should be very careful while learning this, and you should be very keen on some of the points. And let's move further, like how it works. Petrix method as follows. Just I will read it off for your sake, and in just I will try to explain it by taking a problem like how it works. Okay, reduce the prime implicant chart by eliminating the essential prime implicant rows and corresponding columns. Just here we will be having some prime implicant chart. You might be knowing like what is we will be having some of the just I will show it here. So this is a prime implicant chart for your example. Like the here we are having some combinations and what are the outputs with respect to. These are some priority. So you will come to know in next points. Okay, uh, label the rows and label the rows of the reduced prime implicant status p1 p2 p3. Here you have seen it, like what is the uh, pre what is the like priority levels. Okay, then form a logic function p which is true. Okay, and when all the columns are covered, p consists of a product sum of terms, and I will explain this like all the sum of the solution always it should be equal to 1, and it's a known thing for you already. Reduce the p to a minimum sum of products by multiplying out and each and applying this rules. It will be we will be coming across in future problem solving. Okay, each term in the each term in the result represents a solution, that is a set of rows which covers all the minterms in the tables. To determine the minimum solution, to find that those terms will contain the number of variables. Each of these terms represent a solution. In just I will explain you with the problem, so you will try just you read it out once again, So you guys will understand it very clearly instead of explaining it in theory terms. For each term found in step 5, count the number of literals in each prime implicant and find the number of total number of literals. Choose the term which has corresponds to minimum number of literals and write out the corresponding sum applicants. Let's try to resolve it by let's try to understand it by solving a problem which makes more sense. Okay, let's imagine this is our prime implicant table. You all might be knowing how we will get this. One is by using Kuhn-Minkowski method, and other you can, if the number of inputs are less, even you can do it same by using key map also. So as of it's with respect to Kuhn-Minkowski method. So this is the output expression that they have given, and here you can see EB bar AC. Okay, fine. Here both of the results we are having it here. So from this we have to obtain the Petrik's method. We have to obtain the exact solution which represents the first. Okay, these are the prime implicant table. Here you can see this implies with 0 and 1, this implies with 0 and 2, 1 and 5, it implies 2 and 6, 5 and 7, 6 and 7, and I think it's need not required to explain this how we are constructing this table. Hope you guys are already know it with respect to the previous session. And here comes our main topic. Okay, Petrik's method. If all the essential prime implicants and minterms they cover should be removed from the chart. If all the prime implicants and minterms they cover should be, all the essential prime implicants should be removed from this table, and then the label of, okay, should label with the P1, P2, P3, P4, P5, and next topic is we will have a logic function P. Once again we are trying to explain the same thing that we have seen in the previous solutions. Here this topic is very important here. Okay, how we will consider this one? Let's take an example of row 0 sorry, column 0 here, like how it works. Okay, we will try to go column by column. Okay, here you can see this solution 0, how it can be solved. It can be solved by adding P1 and P2. That means 0 represents P1 and P2, right? It can be a P1 plus P2, so that we will have some solution for this 0. And how? So now let's move into the P1 itself. Let's move it to here. Like its correspondence are P1 and P3. So P1 plus P3 may give a result for this first combination. And in the same way, if we move to the next one, here you can see since already we have completed this one, so we'll move out to this one. So this is correspondence to P2. How the result can be obtained to it with P2 along with this P4. P2 plus P4 can give a result for 2. So and in the same way for 5, P3 plus P5 can give the result for 5. That means for the each column present in the table we are trying to get a result. So the same has been explained here. You can see because of the column 0 has a x in the rows P1 and P2, we must choose P1 or P2 in order to cover minterm 0. To get a result for 0, either we should have P1 or is nothing but add. Okay, P1 plus P2, it should give a result. Therefore expression is P1 plus P2 must be a true because we are having some value in that, right? So always it must be a true. And the same it continues for other columns also. So the same thing has been explained here as I have explained till even to cover 7 row. So it should be P5 plus P6 because to obtain a result here it should be like this. Okay, so and this is done. So let's move it and we'll try to understand like how it is. So how many terms we are having? 1, 2, 3, 4, 5, 6 terms we are having. 3 plus 3, 6 terms we are having. So what we are trying to do for each and every column we are trying to get a solution. That's what we are trying to do it here. As I have explained in the same manner, these I have written here and all the results are equals to 1. So all the equation solutions are equals to 1. The expression for the P in the effect means which okay, uh, that means for the expression to obtain the exact expression we must choose between P1 or P2, P2 or P3 or P2 or P4, etc. That means to obtain the entire to obtain the exact expression we must solve this equation and we should get a result. Okay, so 1 minute. How we will solve this? We will be solving this by using this equation by distributive law. So how we got this? Just I was thinking 1 minute. P2 plus 3. Mm, okay, P1. Okay, this is we already know that. Yes, how we are getting that? Yes, yes. Here you can see, just you need to understand it very clearly, like how we got this expression. Okay, this expression, how we have received it. The basic expression, whatever what we are trying to use, this one is this one. How we will get that? You need to understand. And guys, please try to understand this one very clearly. We have to take a common terms between the adjacent terms here. Common term, which is if you take this one, what is the common? It's P1 is common plus still if you want to resolve it still you can do one more thing you guys can do what you can do like just try to take a common here. So what is common here? P1 plus what is left with these two. Here it is left with P2 and P3, just we'll multiply this one, and the same way let's take some other term. So this is done, so it will be a P1 plus P2 into P3. One part will be there, and what is there here? We can see here, we can see, right? So here we are having P4 as a common. In this one we will take a P4 as a common term. Okay, if you take a P4 as a common term, what we are left with? P2 into P6 we are left with. P2 into P6, P2 dot P6 we are left with. Okay, so next let's take this term. So if we take this fourth and sixth term here, P5 is common, so we will take it out P5. So it will be P5 plus P3 dot P6. Hope you are getting. So we are taking out P1, P1 plus P2, P3. So in these two terms we are taking P4, P4 plus P2, P6. In this one we are taking P5, P5 plus P3, P6. The same has been explained here. The same has been written here. So we are trying to take a common term using this term. Okay, x plus y in simple, also using Boolean algebra. If you want to write it, you know this is a Boolean algebraic equation. X plus y plus x plus z equals to x plus yz. If you apply the same rules to those terms, so you will be ending up with getting this result. Try to apply it, the distributive law for the previous expression, and you will be getting that. Is in the same results will be displayed. And how we next from here onwards we will try to resolve by multiplying the equations. We'll be multiplying with these two and these two. You might be knowing the multiplication P1 P4. So we'll try to multiply with P1 P2 P6, then P2 P4 P2 P3 P4 P2 P3 P4. Sorry, then we have to multiply these two, right? So it should be P2 to P2. So it's a P2 P3 P6. So as we can't have a square in that, so it must be a P2. So then we are trying to once again multiply it here. So it will be entirely at the last we'll be ending up with this one P1 P4 P5 P1 P2. Just we are trying to multiply this one with this one. So we'll be ending up with getting this results. We'll be ending up getting with results with this results. Now what we will try to use, what we will try to do, so we will try to have we will try to do simplification by using this functionality. It is x plus y equal to x. Okay, in the sense here you can see it. So this corresponds to this. 1 minute. So this will be this will be this, and okay, we are getting here. So P2, P3, P6, we might be here. You can see P2, P3, P6. We are having one more term here, so it will be 1 plus A equal to 1 only. So if you consider, okay, let's take these two as an example. P2, P3, 6, P2, P3, P6. Suppose if we take it out these two terms, so it will be P2, P3, P6 plus 1 plus P5. What is 1 plus P5? If you remember the Boolean algebra, it is nothing but 1 plus x will be always equal to 1 only. That means these two will reduce into a single term. Got it? So this is one term done. So and next we'll try to get into a one more term where it is P2, P3, P6. Where it is. Just I'm trying to find those terms here. Okay, this is done. And this one we are directly keeping it here as we are left with no terms. So okay, fine. P2, P3, P6. That one we have kept here. P1, P3, P4, P6. P2, P3, P6. P2, P1, P2, P3, 6. Even the same results applies here also. Like you can see, like 1 plus A is nothing but equal to, it will be a same result. 1 plus A is nothing but 1 only. So we will be eliminating it. So and here you can see the same applies here also. P2, P3, P6, P2, P3, 6. That means this all term will combine together and it will make into a single term called P2, P3, P6 by using one single term. 1 plus x equal to always 1 only. So next we will try to use x plus y equal to x to eliminate a redundant from P, which else. So this is nothing but what I have explained. So the same one only. So you can apply one, you can say 1 plus x equal to, you can apply that, or if you apply x plus y equal to x, the results will, and the result will stay the same. Okay. So and this is the final expression that what we got now. Okay, whatever we have received it now. So and in this one there is a one trick here. Okay, here you can see this is the finalized expression, right? This is the finalized output that whatever we have got. If you consider it, we have a 3 implicants here. We have a four priorities here. Sorry, we have a 3 priorities here, and the remaining all we are having a 4. That means in the terms we have to select only the one term. Okay, always which term we have to select, and these terms are individuals, not the dependables. That means this term will be a separate output, and that means in the sense we can say this P is merely having 5 solutions. 1, 2, 3, 4, 5 solutions. 5 solutions. Each term represents each solutions. That if we consider that this is having a 3 implicants, this is having a 4 implicants, this is having a 4, this is having a 4. Once again, this is having a 3. We consider that always the output should be having a very minimum number of results, right? So if we consider that only these two are valid, considering it is having only 3 implicants. So and these are also valid, but they are not considered because they are having 4 implicants here. Okay, so these two are valid, and how we will get the result? So what we will do, we will try to write the result corresponds to this. What is P1 represents to, what is P4 represents, what is P5 represents. In the same way, we will try to write it. Okay, if we consider, if we take a previous table, P1 represents, it will be finally at the, it will be ended with P1, 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 P3, P6. So it will be ended up with having this solution, or it will be ended up having with these solutions. So this one only at the end it will be considered. Okay, the same thing has been explained it here. Hope you guys are getting that. Although there are 5 possible solutions, only 2 have been considered with a minimum number of rows. Okay, thus the 2 solutions with the minimum number of prime implicants are obtained by declining P1, P1, P4, P5 and P2, P3, P6. That represents, so this represents this and this represents this, which are having with 2 solutions. Okay, simplification of incompletely specified functions. Okay, given the incompletely specified function, the proper assignment of values to the don't care terms is necessary in order to obtain the minimum sum of products functions. So whenever we don't have any proper solution or whenever we have received the incomplete solution, that time we need to have the values for the don't care condition. We need to place it as a don't care condition, and we need to obtain the minimum form for the function. And in this section we will show how to modify Quinn-McCluskey method in order to obtain the minimum solution when don't care terms are present. In the process of finding prime implicants, we'll treat don't care terms as if they were required min times. So just with respect to the key map, that whatever we are doing, the same thing will be doing here. They can be combined in order with other min terms to eliminate the many literals as possible. So if extra term implicants are generated because of the don't case, so this is correct because extra prime implicants will be eliminated in the next step anyway. When forming a prime implicant chart, don't case are okay. While doing a prime, and here you need to ensure one thing here. So what is that? While while taking an while doing an expression, we will consider it by, but while taking the prime implicant chart, while writing it in a prime implicant chart, we are not considering it. We are not prime implicant chart, we are not writing it down. Don't care condition, that one always you need to take care while doing this. So we'll solve problem solving. Okay, so however, don't care terms are not included in the final solution unless they have been used in the process of forming one or more selected prime implicants. Okay, so here you can see here we are having some of the don't care terms here. Okay, don't care terms are treated like a required min terms when finding the prime implicants. Here I can see it here 1, 5, and 15 they are considered. Why they are considered? Because these can be considered while doing a problem solving, and it just and based on that, this is the Quinn-McCluskey method that what we are trying to do. So and so just you guys need to be one careful here. We have not written a zeros all zeros combination here. Why? Because our session has started, our function has started with a 1. So always Quinn-McCluskey method, how it will be grouped with the ones, with the 2 ones, with the 3 ones, and with the 4 ones, and it goes on if you have more number of inputs, and it is the way of grouping the number output solution, the Quinn-McCluskey method. So and you guys might be knowing it already, like how we will solve the Quinn-McCluskey method. Like we will start comparing that. So if there is a one term change, one term change, so we will be writing it with a dash, and we will be keep on solving until we get the last iteration in that. So and the same applies. This you can call this as a step 1 and this as a step 2. Okay, you need to ensure that we have covered don't care here, don't care conditions here. Okay, so this is done till this one. So finally we have got a solution here. So these are the final solution that whatever we have obtained. So it is nothing but a b bar d, and if you put terms here, it is nothing but here nothing is there, sorry. It's a b bar d, it's a b bar d, and it's a b bar c, so and it's a cd, and it's a ad. These are the possible solution that we got. And now you remember this 1, 10 and 15. Okay, 1, 10 and 15 are not placed in the prime implicant table. Why? Which will be eliminated as I have explained previously. Those will not be considered here, while those will not be considered while putting into the prime implicants table. This is one way of doing it. So now from here onwards you guys might be knowing like how it can be solved. So just we will try to strike it out which term we need to consider it. Okay, so here you can see, so this is having 137n. As we know that 1 is a don't care condition, we are not writing it here. So 3911, so and remaining thing we 10 is also don't care condition, 2311. So we have to obtain this one, and how it will be considered. So you can see these three, this one with the first one, these three can be covered in other terms also. So now what we will do for that? So for that, so we'll try to eliminate this one, and this has a one prime implicant here. This has a one independent. This also has a one independent, and this also has a one independent. So we'll be taking consideration into this, and these three will be covered in others itself. So the final expected result is B bar C, CD plus AD. So this is the expected results, and you guys have to be very careful with while doing with the final expression of using don't care terms. In the process of simplification, we have automatically assigned values to the don't care case in the original truth table F. That's what we have did. If we replicate each term by final expression for the F by corresponding sum of min terms, the result is something like this we will get. Because of M10 and M15 appear in this expression, M1 does not. This simplifies that don't get terms are in the original truth table have been assigned as follows. Because of M10 and M15 appear in this expression, M1 does not. This implies that don't get terms in the original truth table for F have been assigned as follows. And that means in the final expression whatever we are obtaining, so there we will not be having a values for M1. So only it will be having a value and just in the final expression don't care condition of M10 and M15 are covered. So that final function must be having the results of M10 and M15. And these are some of the problems that you guys have to take care. And this is end of our module. So hope you guys have understood, and please try to go through all the problems which I have shared with, and we have came across many concepts here. So you guys have to recall it. And for the Quinn-McCluskey method, how much to better understanding, I suggest you work on. And with using Patrick's method, I think if you know the Quinn-McCluskey method, you will not face too much of a problem. So, but you should be very careful. And EVM method is also there. So you guys have to be very careful while doing with those kind of a problem. And thank you. And let's end this session. Thank you so much. Bye.